A standard central air conditioning system costs the average homeowner between $11,000 and $14,000 to install, followed by thousands more in yearly electricity and repair bills. And for many people in the developing world, this is a luxury they simply cannot afford. This was the exact dilemma that led an American chemist to make it his life's mission to find a system that could both heat and cool a home using nothing more than the power of nature. And what he came up with was brilliant. Harold Hayes' solution was unlike anything you've likely seen before. A system he proclaimed was the cheapest and most efficient heat storage system for buildings ever devised. It was tested and proven to have the ability to meet a home's energy needs year-round without any machinery, batteries, or even a single watt of electricity. So what is it? How does it work? And why is it unlikely we will ever be allowed to use it in this country? Let's find out. Hayes' system wasn't a new invention, but a refined idea that traces a direct line from ancient survival to modern engineering. Long before the advent of the electric grid, civilizations in Mesopotamia and the American Southwest understood that the most powerful tool for climate control was not a machine, but rather thermal mass. They built with thick earth and stone to soak up the heat of the day, but they were always limited by the speed at which solid materials could move energy. The true lost heritage of managing temperature was a static ancient method that dynamically treated water as a programmable battery, and this was the roof pond. Perhaps the most direct ancestor of the modern roof pond is the Persian Yakhchal. Around 400 BC, Persians developed a method to produce and store ice in the middle of the desert. This was achieved using shallow pools, sheltered by massive walls, on the east, south, and west. These walls blocked the radiant heat of the sun and stilled the air, allowing the water to lose energy through long-wave radiation to the unheated space of the night sky. The success of the Yakhchal was predicated on the understanding that the night sky acts as a deep heat sink. Even when the ambient air temperature was slightly above freezing, the radiative exchange between the water and the clear sky was sufficient to produce ice. This mastery of nocturnal radiation forms the scientific basis for the modern systems developed centuries later. In 1952, Harold Hay, an American chemist and building researcher, was stationed in India as part of a post-war development program. He arrived to find a housing disaster. Traditional thatch and mud roofs, which provided natural insulation, were being systematically replaced by modern asbestos cement sheets. While these new materials were durable, they offered no thermal insulation. They turned homes into ovens during the day and iceboxes at night, causing immense physical suffering for those who could not afford fans or heaters. Hay realized that modern industrialization had traded human comfort for mass production and profit. Determined to find a low-cost solution, Hay spent the next 2 decades moving from the heat of India to the deserts of Latin America, obsessively testing how to manipulate the temperature of a building. It was during this period of experimentation that he observed the merits of applying movable insulation in combination with the thermal properties of water. By the 1960s, Harold Hay had refined his vision of passive climate control into the perfected Skytherm system, a sophisticated hybrid technology that leveraged the high specific heat capacity of water combined with movable insulation to regulate interior environments. Hay conducted preliminary experiments in Arizona in 1966 and 1967 with 2-foot square, 7-inch deep water basins. Horizontal insulation covered the basins during the day, and the water was exposed to the sky at night. Results indicated that 6 inches of water provided adequate thermal storage for year-round air conditioning. After several attempts at branding the system under different names, Hay would eventually coin this strategy as the roof pond system. Hay's experiments with water in Tempe caught the attention of the revered passive solar engineer, John I. Yellett. Thanks to Yellett's belief in the roof pond concept, Hay received an opportunity to test his theoretical system in a full-scale test building in the Sonoran Desert. But before we get to that, if you want to understand how a roof pond works, you have to stop thinking of a roof as a shield and start seeing it as a sponge. Unlike a standard home with an attic, a roof pond house uses a ceiling made of a heavy, conductive material like steel or concrete. Resting directly on top of this ceiling are large, heavy-duty plastic bladders filled with several inches of water. This water acts as a thermal battery, essentially a massive storage tank for heat. And the overarching principle that allows this entire system to function is a physical law called nocturnal radiation. This is the natural process where any warm object on Earth sheds its heat toward the absolute cold of deep space. On a clear night, the universe acts like a giant vacuum, sucking heat away from the planet. The roof pond is designed to make maximum use of that effect. In the summer, this cycle starts in the morning. Before the sun hits the roof, a set of thick, motorized insulation panels slides across the water bags, sealing them off from the sky. As the sun beats down, the reflective panels deflect the solar heat away, using the albedo effect to minimize the amount of heat transferred to the water bags. Inside the house, however, because the water bags are resting directly on the metal ceiling, they begin to soak up the rising heat from the rooms below. The water acts as a heat sink, pulling the warmth out of the air and storing it. By the end of the day, the house is cool, and the water is warm. When the sun sets, the insulation panels slide open, exposing the warm water to the night sky. And because there is no sun to push heat down, the water begins to offload its stored heat upward into the cold void of space. By dawn, the water has been chilled back down to a refreshing temperature, and the insulation panels close to start the process over. In the winter, the journey is reversed. The insulation stays open during the day, so the water can soak up direct heat from the sun. At night, the insulation closes to trap that warmth inside. The water then radiates that heat downward through the metal ceiling, warming the house through the night without a single flame being lit or a single vent blowing air. It is a silent, heavy, and eternal cycle of energy moving from the earth to the stars and back again. And the effectiveness of roof pond technology is not merely a theoretical claim. It is supported by decades of rigorous data from some of the most respected architectural and engineering institutions in the United States. The most significant case study of this technology was Hayes Skytherm House in the Sonoran Desert, a project monitored extensively by California Polytechnic State University and funded in part by the U.S. Department of Housing and Urban Development. For over a year, researchers recorded every temperature shift, and the results were staggering. During a summer where outdoor temperatures reached 100 degrees, the indoor temperature remained between 66 and 74 degrees, without a single watt of mechanical air conditioning. In the winter, while outside temperatures dropped into the 30s, the home stayed at a comfortable 70 degrees, using only the solar heat stored in the water. This study proved that a properly designed roof pond could provide 100% of a home's heating and cooling needs in a Mediterranean climate. Beyond residential use, the scalability of this technology has been explored for industrial applications. Research conducted by the Passive Solar Journal and the American Solar Energy Society has analyzed how roof ponds can be used to stabilize temperatures in large warehouses and factories where the cost of cooling is often the highest operating expense. In these larger contexts, the system solves a high-stakes problem. It eliminates the peak load demand on the electrical grid. When thousands of standard air conditioners turn on at 2 in the afternoon, it causes brownouts and forces the use of expensive, dirty, peak power plants. A roof pond system, however, operates during the night to dissipate the heat that it has collected during the day. By removing the energy demand from peak times, roof ponds provide a path to a more stable and resilient energy infrastructure that can handle the intensifying heat waves of the modern era. So not only do they help the residents, they also help grid operators. So why don't we use them? To answer that, you have to understand that a roof pond creates a massive barrier called a split incentive. As it is with many of these passive systems, the people who build houses want to keep their upfront construction costs as low as possible, so they can maximize their profit on the sale. A roof pond requires a house to be built with significantly more strength than a standard home. While a typical timber-framed roof is designed to hold about 40 pounds of weight per square foot, a roof pond requires a structure capable of holding nearly double that amount to account for the massive weight of the water. Developers are unwilling to pay for the extra concrete and steel reinforcement required for a heavy roof when they can instead install a cheap, lightweight air conditioning unit for a fraction of the initial cost. Instead, they pass the burden of the high electricity bills and future repair costs onto you. A roof pond is a permanent structure, which means there is almost nothing that can be sold to the homeowner in terms of additional services. There are no complex compressors to burn out, no chemical refrigerants to leak and refill, and no specialized computer boards that require a licensed technician to reset. For a manufacturing industry that relies on planned system failures and a service industry that relies on recurring maintenance contracts, the roof pond is a financial dead end. Therefore, our entire regulatory system has evolved to support this lightweight, high-energy model. Building codes are written with specific prescriptive paths that make it very easy to get a permit for a standard house with an AC unit, but incredibly difficult and expensive to approve a gravity-loaded thermal mass system. Another bureaucratic barrier here is that most local building departments simply don't have the staff trained to calculate the safety of a water-integrated roof, leading to endless delays and custom engineering fees that scare away all but the most dedicated owner-builders. So we continue to use energy-consuming machines not because they are better, but because the construction industry and their advisors are optimized to sell us a product that is designed to be cheap in terms of capital cost and convenient to use. But there are also practical limitations to Hayes roof ponds that should be mentioned here. During his prototype tests, the insulation panels commonly caused malfunctions. Poor seals along the edge of the movable insulation resulted in major thermal leaks. Water leakage was always a concern too, although a low-sloped roof system should easily overcome this issue. But if you are ready to move beyond the theory and begin implementing a roof pond, you must first understand that your options are dictated by the structural limits of your building. Because the technology relies on the thermal mass of water, there are three primary paths to bringing this into reality, ranging from a simple interior modification to a professional ground-up build. The most accessible starting point is the interior thermal barrel method. This requires no structural reinforcement and can be done in any existing room with a south-facing window. The process involves placing several large, dark-colored barrels filled with water directly in the path of the sunlight. In this setup, your window coverings, curtains, or blinds act as the motorized insulation. During summer, you keep the curtains closed during the day to keep the sun off the barrels, and at night, you open the window and the curtains, allowing the heat in the water that was soaked up from the room to radiate out into the night sky. In the winter, you do the opposite. You open the curtains during the day so the barrels can absorb the sun's heat, then close the curtains at night to trap that warmth, allowing the barrels to radiate heat into the room for hours. This is the simplest path. It is not a roof pond per se, but it uses the same principles. For those looking for a more permanent integration, the second path is the experimental retrofit. Ideal for an off-grid cabin or workshop, a simplified roof pond can be integrated using high durability materials. The roof should be framed with a raised curb, 6 to 12 inches, around the perimeter. This tub must be lined with a heavy-duty, 45 mil or 60 mil EPDM pond liner. Unlike thinner materials, EPDM is designed for permanent water immersion and UV exposure. Using individual water bladders is recommended over an open pond to minimize evaporation and sloshing during seismic events. Professional-grade UV-inhibited polyethylene bags are the standard, sometimes referred to and sold as pillow tanks. For a budget-friendly alternative, some off-grid builds utilize black poly pipes or modified IBC totes, though these lack the surface area contact of a true thermopond. For the insulation, rigid polyurethane or XPS foam panels are a good choice, R15 to R30, framed in aluminum or treated wood. These can be mounted on heavy-duty barn door-style tracks. A manual rope and pulley system is the most reliable for off-grid use, though a simple 12-volt actuator powered by a single 100-watt solar panel and a small battery can automate the cycle. Finally, it is advisable to install overflow scuppers at the max fill line. If the pond is 10 inches deep, the scupper should be at 11 inches to ensure that heavy rain cannot overtop the curbs and add dangerous weight to the structure. This is also viable for buildings with existing flat, over-engineered roofs, such as shipping container homes or industrial workshops. The most difficult aspect of this build is constructing a frame and track system for sliding the rigid foam insulation panels. The final and most effective option is the ground-up load-bearing build. This involves designing a new home specifically around the weight of a full roof pond. To support this, you must use reinforced concrete or heavy-gauge structural steel. The roof becomes a high-strength deck that serves as both your interior ceiling and the floor of the pond, creating a seamless thermal bridge. While the physics are simple, the honest barriers are always weight and water leakage. Water weighs approximately 62 pounds per cubic foot, adding over 30 pounds of dead weight to every square foot for even a shallow pond. Whether you are placing tanks or bladders on the roof, you must consider the mass on your structure loadings and apply proper water sealing to the approved standards for flat roofs. But for those who do, the reward is a lifetime of thermal comfort with a significantly reduced utility bill. By leveraging the thermal mass of water and the law of nocturnal radiation, we can eliminate grid-dependent climate control and replace it with a permanent, zero-cost structural battery. This is a mission to stop buying our energy from utility companies that are focused on profitability and to help those who are interested start building their own energy independence. If you enjoyed this video and want to learn about another passive cooling system you can incorporate into your building, then make sure to check out our latest video on solar chimneys.